welcome to Chem 104. This is the first lecture in the first module, and because of that, I want to go over a few logistics. We'll let this Bunsen burner draw on the side of the page. First thing, there is a PDF document that's located after this video in the content section of the module. You're going to find a PDF document after every lecture video in the course. This document contains an outline of the lecture material. It is very strongly suggested that you print it out, use it to take notes as you follow along. The second thing is that there is a pause button on this video. You can stop it, you can rewind it, you can rewatch it anytime you want. Definitely do this as many times as you need. There will be also times during the video that I actually ask you to push the pause button. I have questions that I want you to answer, and you will get more out of the lecture if you stop the video and answer the question to the best of your ability, and then let the video go on and you can check your answer. You can see what answer we arrived at. This will help you come up with questions that you need to ask during online office hours, or it might help clear up confusions that you have. You will get much more out of every lecture if you do this. Okay, so now that we've talked about all those logistics, let's look at this chemistry that's going on. See, we have this water that's being heated up by this Bunsen burner. What's happening here? See, as the water heats up, oh, there's bubbles. The water boils. The water has changed. Chemistry has happened. And so, some people call chemistry the study of change. We could also say that chemistry deals with the structure, properties, and transformation of matter. Now, we're going to take the whole quarter to really delve into what we mean by that definition. So, we're going to start exploring with a question for you. See this little guy? His name is Thinker Buddy. When he pops up, you'll want to pause the video and answer his question. When you've answered it to the best of your ability, press play and move on to see the answer we arrived at. So, Thinker Buddy's first question is, how does chemistry affect your daily life? Go ahead and pause the video, and we'll come back and talk about it. Okay, so how does chemistry affect your daily life? There's a lot of answers that you could have put down. Most of you, I think, are going into the medical fields, so maybe you would have said something to do with health and medicine. There's even many possibilities within health and medicine. We know that sanitation systems use chemistry. Anesthesia during surgery uses chemistry. We have vaccines, we have antibiotics. Those all use chemistry. Maybe you said something about energy and the environment. There's a lot of chemistry there. We burn fossil fuels every time we drive a car. Some of us use solar energy. We have solar energy panels. There are nuclear energy plants. All of those use chemistry. We use materials and technology every day that use chemistry. We use polymers in our plastics, ceramics. We have liquid crystal displays on our watches. Someday, we really want to be able to use room temperature superconductors. Or maybe even molecular computing. That would be fantastic. We have food that we eat every day, and it all involves chemistry. Even the farming and the agriculture of growing the food. There's some controversial topics in this that deal with chemistry. We have GMO foods. We have pesticides, natural pesticides, synthetic pesticides. We have fertilizers. All of those deal with chemistry. There's a lot of chemistry that goes into growing our food. These are just a few answers. You could have had many different answers. And I'm sure that you thought of many that I didn't even think of. You might be wondering how chemists come up with all this stuff. How do they find new polymers? How do they plan to go about developing molecular computing? It also sometimes seems like science changes its mind all the time in the news. One day something is good, and the next day something is bad for us. Trans fats, for example. It seems like scientists are constantly challenging our beliefs about science. They're always asking questions, and they're always experimenting to gain new knowledge. And how do they go about doing that? They use something that we call the scientific method. It is a systematic approach. That's the most important thing, that it's systematic. And it involves some steps that you're probably somewhat familiar with. Usually the first thing that happens is an observation. You probably make these kinds of observations in your everyday life. Let's say you're an avid gardener. You may notice that some tomatoes in your garden are bigger than others. And then from that observation, you would come up with a hypothesis. A hypothesis would be a tentative explanation for your observation. Your hypothesis can change over time. It's just an educated guess about what's happening. You might say, I think the tomatoes that get more sunlight grow bigger than the ones that get less. And then you would perform an experiment where you gave a certain set of tomatoes more sunlight, another set less sunlight, and gave them all the same care besides the sunlight. And you would see what the results of your experiment were. Did your experiment hold up your hypothesis? You're going to make some observations about that. Go back to the beginning. You might have to change your hypothesis. Do another experiment. Go back to the beginning. Make more observations. Refine your hypothesis. After you go through this loop many, many, many times, you can come out of it with a scientific law. A scientific law is an explanation of what happens in science. We have some, like the law of gravity. It describes what gravity does. It pulls things toward the earth. It doesn't really tell us anything about why it happens. That is a theory. A theory is a model of why something happens. By the time you develop a theory, you have gone through the scientific method, through this loop, thousands and thousands of times. A theory is a well-tested hypothesis. It is not a guess in any way. It's a little different than the way we use theory in our everyday speech. With the theory, you can make a prediction, and you can predict what will happen in an experiment. Then run the experiment. See if your prediction is correct, given your theory. If it is, you don't need to modify your theory. If it isn't, you may need to modify your theory a little bit and go back through the cycle. You'll see there's a lot of loops in the scientific method. This is why, from the outside, it often seems like scientists are changing their mind, but in reality, they're just modifying their explanations. They're refining their ideas. It's a fundamental part of science. Here's Thinker Buddy again. So, I want you to make an observation about something in the room, propose a hypothesis, and plan a really brief experiment to test your hypothesis. You don't have to be really detailed. I just want you to think about how you might go about using the scientific method to answer a question in your life. So go ahead and pause the video, write this down, and come back. So, now that you're back, I assume that you came up with a question you wanted answered. Oftentimes, when we're trying to answer scientific questions, we need to make measurements. Maybe your experiment needed measurements. That tomato experiment certainly did. We have to measure the diameter of each tomato. When you're taking a measurement, what are the two parts to a measurement? I want you to pause the video and think about that for just a second. So let's say we have a measurement like 12 feet. There's a 12, which is the number, and there's feet, which is the unit. It's really important that we have both parts. The number 12 doesn't mean anything unless we know that we're talking about feet. In chemistry, we almost always use metric units, so we typically wouldn't use feet. We would say something was 2.34 meters long, because a meter is the basic metric unit for length. And there are base units in the metric system for each type of measurement you might take. For length, it's a meter. For volume, it's a liter. For mass, it's a gram. For time, it's seconds. For temperature, it's degrees Celsius. And for energy, it's calories. When we want to measure something, like amount of something, we use a unit called a mole, which may not make a whole lot of sense to you now, but you'll see it again later. So those are the metric units that we'll typically encounter. And we will also encounter some other units, just so you have a good list of them and you can refer back to this video and to your notes. Here are a few common units for distance and volume and weight and mass and time and energy. It's good to know the abbreviations for each of the units so you can easily recognize them. So now that we know about measurements, let's say we wanted to measure the number of atoms in 12 grams of carbon. What would that be? It's a whole lot of pencils, all of that carbon. Turns out that would be 600,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000. It's a really big number. What if we wanted to measure the mass of a single carbon atom in grams? Well, that's going to be 0.000000000000000, and I think I've lost track of zeros, 199. It's a really small number. These numbers are completely unreasonable to deal with when you're trying to do calculations. There's no way you can keep track of all of these zeros and not make a mistake. So it's much easier to write these numbers in what we call in scientific notation. This first number up here becomes 6.022 times 10 to the 23rd. So much more reasonable. The second number we have becomes 1.99 times 10 to the minus 23rd. In science, we often encounter these really big and really small numbers, and we need to know how to write numbers and deal with numbers in scientific notation. Let's say we have a number like 568.762, and we want to write this number in scientific notation. The first step is to move the decimal somewhere in the number that will create a number between 1 and 9.9999. In this number, we would have to move the decimal between the 5 and the 6. So we have to move the decimal left 2 spaces. This gives us the number 5.68762. And then in scientific notation, we always write times, with an X, 10, and that 10 is raised to the power of 2 in this case. That number comes from the number of spaces that you had to move the decimal. And in this case, the exponent is positive. And that is because we moved the decimal left. There's a fun way to remember this, and we can think of a map, and when you move to the left, you're moving toward the west coast. We live in Portland. We know that moving toward the west coast is a positive move. Therefore, when you move left, you have a positive exponent. Okay, Let's try a smaller number, a number smaller than 1. 0.000000772. So the first step is to create a number between 1 and 9.999. So we have to move that decimal place 6 spaces to the right, so it's between those two sevens. And then we get 7.72 times 10, and we moved over to the right, so we get a -6. The 6 comes from the number of spaces we moved over, and the exponent is negative because we moved to the right. And again, a good way to remember this is moving to the right is moving toward the East Coast on a map, and we all know that that's a pretty negative move. Now it's your turn to give it a try. Why don't you try to place the following numbers in scientific notation? Go ahead and pause the video once you can see all 4 numbers. Okay, welcome back. Well, here are the answers to those 4 problems so that you can check your work. In the answer to that last one, 1.000 times 10 to the second, why did we keep all those zeros? Why didn't we just say 1 times 10 to the second? Did we have to keep all the zeros? Turns out we did. In scientific notation, you have to keep all the digits that are significant. Significant digits or significant figures. What do we mean by that? Sometimes we call them sig figs for short. Before we get into the nitty-gritty of sig figs, let's go back to the measurement. How do we measure anything? How do we measure length or volume or mass or time or temperature? What do you think? Go ahead and pause the video and think about this one for a minute. Length is a pretty easy one. We measure that with a ruler, right? And in chemistry, since we're using the metric system, our ruler will be in meters or centimeters, not inches. How do we measure volume? We use something called a graduated cylinder. There are a couple other items we can use in chemistry to measure volume, but one of the most common is called a graduated cylinder. It's a long, skinny tube, glass tube that we'll use. How do we measure mass? We usually use something called a balance. We measure time with a watch or clock, and we measure temperature with a thermometer. So you probably knew the answers to these really easily, but it turns out that the device we use to measure has really big implications on the actual measurement. So here we have an arrow, and we have 2 different rulers. How long is this arrow? You'll see that the ruler on the top only has markings in centimeters, and the ruler on the bottom is marked in centimeters, but there are designations for every 1/10 of a centimeter. Does that make a difference in how long this arrow is? Take some time and think about how long would the arrow be with the top ruler? How long would it be with the bottom ruler? Once you have a good answer, go ahead and play this video again. So I would say with the top ruler, we know that the arrow is between 1 and 2 centimeters. And by looking at it, we can guess that it's about 1.7 centimeters. That 7 is actually a guess digit. And with this ruler, our guess digit is in the 1/10ths place. So now let's look at the bottom ruler. We can see that the arrow is somewhere between 1.6 and 1.7. And in this case, we can guess another digit. We could say it's a little past half, and so it's probably close to 1.67 centimeters. With this ruler, our guess digit is in the 100ths place. any measurement that you or someone else makes has an uncertain last digit. We call that the guess digit. You should always make an educated guess at that last digit that you don't know for sure. You usually know within plus or minus 1, so we know that the first measurement is between 1.6 and 1.8, and we're guessing that it's 1.7. So we said that this measurement device had an impact on the number of significant figures in our number. Now let's take a look at what a significant figure is. The definition of a significant figure is the numbers in a measurement that represent the certainty of the measurement, plus one number that is an estimate at the end. So our first measurement was 1.7 centimeters. That number had a 1 for sure, and then a guess digit of 7. It has 2 significant digits. The second measurement was 1.67 centimeters. It has 2 digits that we're certain of, 1.6, and then it had 1 digit, the 7, that was the estimate. So this number has 3 sig figs. So we see that depending on the device that we use, our number of sig figs will change. In the first case, we only had 2, and in the second case, we had 3. So the more precise the instrument that we use, the more sig figs we get in our measurement. It's usually pretty straightforward to determine sig figs when you're the one taking the measurement, but what if your lab partner comes to you and tells you that she measured the volume of water in an experiment to be 0.600 liters? How many sig figs does that number have? Why don't you pause the video, think about it for a minute, and then come back and join us. Welcome back. So the answer is 3. If you didn't get the right answer, don't worry. We haven't gone over the rules yet. Now we're going to actually learn why. But it's always good to think about these things ahead of time. So there are some rules for determining significant figures. The first rule is any digit that is not 0 is significant. This means anything that's not 0 in your number is a significant digit. If you have 1.234 kilograms, you have 4 significant digits. It turns out that the zeros are really the tricky part, and the reason the zeros are tricky is because 0 can either be a placeholder to move things around, or it can actually be a 0. That means there's 0 things in this column, and not just a placeholder. And so we have all of the rest of the rules tell us about these zeros and whether they're significant. The second rule says that zeros that are between non-zero digits are significant. This means if you have a number like 606 meters, that 0 that is between the two sixes is significant, and you have 3 sig figs in that number. The third rule says that zeros to the left of the first non-zero digit are not significant. So if we have a number like 0.08, that 8 is the first non-zero digit. And those other zeros are to the left of the 8, and they are not significant. So this number only has 1 sig fig in it. The fourth rule says that if a number is greater than 1, then all of the zeros to the right of the decimal point are significant. So if you have a number like 2.0 milligrams, that 0 is to the right of the decimal point, and that whole number is greater than 1, so it is significant. And so that number has 2 sig figs. The last rule says that if a number is less than 1, then only the zeros that are at the end and in the middle are significant. So if we have a number like 0.004020 grams, those first 3 zeros are not at the end and in the middle. They are to the left of the first non-zero digit, so those are not significant. But the other zeros are in the middle and at the end, and so they are significant, and this number has 4 sig figs in it, 4 significant digits. Now I want you to give it a try. So here are 5 numbers, and using the rules on the left, I want you to pause the video and take some time to think about it and figure out how many significant figures are in each of these numbers. Welcome back. And so now let's take a look at the answers. The first one, probably pretty straightforward, was 4 sig figs. The second one has 5 sig figs. All 3 of those zeros are between non-zero digits, so they are all significant. The third one, 0.0320, has 3 sig figs, 320. The fourth one, if you recall when we were talking about scientific notation, we said that when we write a number in scientific notation, we have to keep all of the digits that are significant in our first number. And so when a number is written in scientific notation, it's pretty easy to tell how many significant figures you have. You can just count all of the numbers in the first number. So those last 3 zeros, because the number is greater than 1 and they're to the right of the decimal place, are significant, and this number has 5 sig figs. The last one was the trickiest, 56,000 kilograms. We do know that it has at least 2 sig figs, 56, the 5 and 6. But what about those last 3 zeros? We don't really have a rule about them. And there's no way to know from the way that the number is written if the measurement device could measure 100's place or if it couldn't. I mean, maybe there really was a 0 in the 100th place and the measurement device could measure it. Maybe it could measure to the 10's place and there really was a 0 there and it's significant. We don't really know from the way it's written, so we only know that there's at least 2 sig figs. One way to know for sure would be if the person who took the measurement wrote it in scientific notation. Then we would know for sure how many sig figs that number had. I'm sure you're dying to know how to use significant figures in calculations. I mean, what about calculations? We have to know how to add and subtract. You know, there are significant figure rules for addition and subtraction. It turns out addition and subtraction are treated the same way, and there is just one rule that covers both of them. We will talk about multiplication and division later. For addition and subtraction, the answer cannot have more digits to the right of the decimal point than any of the original numbers. There's a big hint here. Always line up addition and subtraction problems vertically if you want to figure out the significant figures in your answer. So here we have an example problem. We have 89.332 plus 1.1. This is easy to add up. You get 90.432. But that's not your answer. You have to figure out how many significant figures are in your answer before you report it on a lab report or in a homework assignment. And since this is an addition problem, we look to see which number has the least number of digits after the decimal point. And we see that this 1.1 only has 1 significant figure after the decimal point. And that means that our answer can only have 1 significant figure after the decimal point. And so we have to round it to 1 digit after the decimal point. So the answer to this problem is 90.4. If you answer 90.432, it's incorrect. The answer is 90.4. Let's try a subtraction problem. So here we have 3.70, and we don't know those next 2 digits, minus 2.9133. Notice we're still lining them up vertically, so all of the columns are in a nice straight line. This number, it's really easy. We can put it in a calculator and we'll get more digits after this 0.79. However, those digits, we don't know those last two digits because in our subtraction problem, that first number only had two significant figures after the decimal point. And so our answer has to be rounded to two digits after the decimal point. So the answer to this problem is 0.79. Now let's move on to some multiplication and division. So just like addition and subtraction are treated together, multiplication and division are treated the same way. So the sig fig rule for multiplication and division is that the number of significant figures in the result is set by the original number that has the smallest total number of significant figures. This rule is actually the one that most people find the easiest. You just need to look at the numbers in your problem. Whichever one has the least number of significant figures, that determines how many are in your answer. So if we have a problem like 4.51 times 3.6666, we can see that 4.51 has only three significant figures. It's the smallest number of significant figures in our problem, and then we have to round our number to 3 sig figs. Not 3 sig figs after the decimal point, 3 total sig figs. So that gives us 16.5, 3 significant figures. Let's try a division problem. If we have 6.8 divided by 112.04, we get a really long answer out of our calculator. But we can see that 6.8 only has 2 significant figures. That's the smallest number of significant figures in our problem. And so we have to round our answer to 2 significant figures. So our answer is 0.061. The 6 in the column to the right of the 0 tells it to go up. So we get 0.061. 2 significant figures in the answer. We are almost at the end of this first lecture in the first module. So this is the last Thinker Buddy for this lecture, so hang in there. I want you to work through these problems. Try to determine the answer. Make sure that you obey the significant figure rules we just went over. So go ahead and pause the video, work through the problem, see what you get, and then we'll come back and we'll go over the answer. Welcome back. So how'd it go? I hope it went well. So the answer to the first problem is 23.5. It's an addition problem and it's written horizontally. Remember to line it up vertically first. And if you line it up vertically, you'll see that 15.2 has the least number of digits after the decimal, only 1, and so the answer has to have 1 digit after the decimal. The answer to the second one is 4.20 times 10 to the 2nd. This one was tricky. That's why there's a hint for you. When you line this up vertically, you can see that 4.20 times 10 to the 2nd, when you write that number out, and you'll always want to write the numbers out, not in scientific notation when you're figuring out addition and subtraction rules for significant figures, that doesn't have any digits after the decimal. So the answer can't have any digits after the decimal. And so that is why you end up with 4.20 times 10 to the 2nd. Last one is a division problem. And so we just have to look and see which number has the least number of significant digits, and that is the same as the significant digits in the answer. And we see that 1.2 times 10 to the 3rd only has 2 significant digits, and so therefore our answer only has 2 significant digits. So you've reached the end. I hope it was a good experience for the first lecture. There is another lecture, 1B, in this module, just to complete the material. It's a little bit shorter than this one. I will see you there. Bye.